So we have been looking at derivatives and finding out where a function is increasing and decreasing by looking at the derivative. And so now we're looking at more with taking the second derivative and learning more about the graph with the second derivative. So there's a few documents that I found, except it did not go well in my last class when I was writing on a PDF. So I don't really want to do that with your class. So I'm going to stick with my Word document. And I'm going to just pull a little bit of this and put it on the Word document. And then let me get that bigger. Oops, too big. Okay, so let me just kind of read through what that top says. So we've already seen about locating intervals in which functions are increasing and decreasing, and that helps us describe the graph. In this section, we'll look at locating the intervals in which the derivative is increasing or decreasing can be used to determine when a function is curving upward or curving downward. And so there's multiple ways to see when a graph is increasing, decreasing, or finding max and mins. But notice there's different things called, it's called concavity. And the graph can either be concave up or concave downwards. And we can find our concavity by looking at the second derivative. So let f be differentiable on an open interval. So it has to be we should be able to take the derivative of it. The graph of f is concave up on I if f prime is increasing on the interval, and concave down on I if f prime is decreasing on the interval. This was something that I've never actually noticed, which is kind of cool. To be able to look at a function, looking at where you would put the tangent line kind of shows you if it's concave up or concave down. So it's concave up, and I never knew this before, if the tangent line, when you're drawing it on the graph, has to be below it. And it's concave down if the tangent line, when you draw it on the graph, is above the curve. Okay, so if we're going to try to find the concavity of some function, then we need to find the second derivative. So you're taking the derivative twice. And once we've done that, we want to figure out when is the second derivative equal to 0 and when is the second derivative undefined. So similarly to what we were doing when we were trying to find if it was increasing or decreasing, we were looking at the first derivative and setting it equal to 0 and where it's undefined. So once we've done that, those are like our critical numbers, and we want to make a sign chart. So we're going to put those on the number line, just like we did with the first derivative. And we're going to put those numbers we found and on there, and we're going to test numbers above or to the left and the right of these numbers to see if our second derivative is positive or negative. If the second derivative is positive, that tells us the function is concave up on that interval. And if the second derivative is negative, that tells me it's concave down on that interval. Okay, so let's look at this example. You're given that f of x is 4x cubed plus 21x squared plus 36x minus 20. Okay, so let's find the second derivative of f of x. And so first thing that we're going to do is we know to first find the first derivative. So using our general power rule, so 4x cubed, bringing our power down and multiplying it to the 4. So 4 times 3, that gives us 12x. Subtract 1 from the power, it's now squared. Plus, so 21x squared derivative would be 21 times 2, so 42. Subtract 1 from the power, you get x. Plus the derivative of 36x, which is 36. And derivative of constant is always 0. So finding the second derivative, all we're doing is taking the derivative of what we just found above. And so derivative of 12x squared, well, 12 times 2, so that's 24x. And the derivative of 42x is 42. And the derivative of 36 is 0. So we want to find where the derivative, second derivative is equal to 0 and undefined. Well, I can tell by looking at the second derivative, this is a polynomial. There's no radicals, there's no variables in the denominator. There's no natural log. And so it's defined everywhere. There's no trouble spots. And so there's no place where it's undefined, but we can look at when the second derivative is equal to 0. That would be when 24x plus 42 is equal to 0. So solve for x, subtract 42 on both sides. Get x by itself, divide both sides by 24. So we get negative 42 all over 24, which I notice reduces. They both are divisible by 2. So that would be 21/12. Well, I also notice those are both divisible by 3. So that is 7/4. So that is like my critical number, but to test for concavity. And so we put that on the number line. And we need to test into the second derivative, a number on the left and the right of that number. Oops. So if we choose some number to the left of negative 1.75 or negative 1 3/4. So sorry about that. How about x equals negative 2? So plug in negative 2 wherever you see an x, you have 24 times negative 2 plus 42. So we have negative 48 plus 42, which is negative 6. So this is less than 0. So if it's less than 0, it's concave down. If it's concave down, it's facing downwards like this. And so now we need to see what's going on the right-hand side. And so if I choose a number to the right, so maybe x is equal to 0. And so if I plug in 0 into the double derivative, we get 24 all times 0 plus 42. So this gives me 42, which is greater than 0. So that tells me that my graph is concave up. So if your function's defined at the value that we found, which is our critical number, which it is, and it changes concavity, then that point is called, where it changes concavity is called an inflection point. So if a graph is defined, or maybe not a graph, a function, is defined at, I don't know, let's say x equals c. And it changes concavity. At x equals c. Then let's call it the point C, f of c. Is called a inflection point. So if they ask me to find this point, I haven't found the point. I have found the x value. I haven't found the y value. So plug C into the original function. Oops. So in our case, if I'm going to plug that back in to my original function, I'm not going to put it in that form I written it. I'm not going to leave it as -1 3/4. I need the original function. Oops. Darn it. Okay, so for original function, sorry, I need it down here. We have 4x cubed plus 21x squared plus 36x minus 20. And we need to go back in and we need to plug in negative 1.75. So 4 times negative 1.75 needs to be in parentheses and then cubed. Then plus 21, parentheses, negative 1.75, in parentheses, and then square it. Plus 36 times negative 1.75 minus 20. So if I did this right, I get negative 40.125. Oops. So my inflection point is at negative 1.75, comma, negative 40.125. Okay, so looking at that, let's go, I don't know. Let's find out where it's increasing and decreasing. Actually, before we do that, because my math lab is going to ask you, so what interval is it concave up and concave down? Well, on the left of negative 1.75, the second derivative was negative, and so it's coming from negative infinity to negative 1.75. It's concave down. And then on the right-hand side of negative 1.75 to infinity, it was concave up. So where is f of x increasing and decreasing? Okay, so we needed to find the first derivative for that. So we need to find when is f prime of x equal to 0 and when is f prime of x undefined. So we already did that work from above. We already took the first derivative. So let's go back over here. Let's snag it. We can. Darn it. Okay, let me just write it down. 9 equal to 12x squared. It's 42x. I could have just done it faster by just looking at the derivative. So we found the first derivative was 12x squared plus 42x plus 36. We want to know, when is this equal to 0? First thing I would probably do is try to factor it. I notice that 6 goes into all 3 of those terms, so I can pull out a 6. That would leave me with 2x squared plus 21x plus 18 equals 0. So I need to either try to factor 2x squared plus 21x plus 18, or I need to use the quadratic formula on that.
If you
Unfortunately,
pull
my
6 out of 42, you get 7.
Oops, thank you. Yeah, you do. Okay.
And 18 would become 6.
What was I thinking? I was dividing by 2
You're
there.
pulling 2's out.
Yeah. Thank you. So that would be 6. So I'm just thinking to myself, because I have to do my AC method. So what multiplies to give me A times C, which is 12, and would add to give me my middle term, which is 7. And I noticed that there are 2 numbers that do that. That's 3 and 4. And so let's just do this on the side. Let me just try factoring this. So I'm going to factor this inside parentheses here. And so I can rewrite my middle term of 7x with 3 and 4. So this will be plus 4x plus 3x plus my 6 here. And I'm going to factor by grouping. So I can pull a 2x out of the first 2 terms, which gives me x plus 2. And I can pull a 3 out of the last 2 terms, which leaves me x plus 2. So this factors as x plus 2 times 2x plus 3. So I have 6 times 2x plus 3, all times x plus 2 is equal to 0. So 6 never equals 0. 2x plus 3 is going to equal 0 if we subtract 3 and divide by 2. So we get negative 3/2. And x plus 2 equals 0 when we subtract 2, we get x is negative 2. It's never undefined, so these are our critical numbers. And we want to test on each side of them to see if we have a positive or a negative number. And we're testing it into the derivative function. And so if we write a number line, we had negative 3/2 and negative 2. So negative 2 is on the left. And we have negative 1.5. And so if we choose something to the left of negative 2, so negative 3, and we plug it back into the first derivative, we want to see, is it positive or negative? I don't really care what the number is. I'm just curious, is it positive or negative? Well, 6 times 2x plus 3. So x is negative 3, all times x plus 2. So if we just think about multiplying positive and negatives just to see if the result is negative or not. So 6 is positive, 2 times negative 3 is negative 6 plus 3. So that's a negative number. All times negative 3 plus 2, which is a negative number. So this is equal to a positive number, which is greater than 0. So on the left of -2, our graph is increasing. So choose a number in between -2 and -1.5. How about -1.75? Or actually let's just do -1.8. So plugging it into the first derivative, we have 6 all times 2 times -1.8 plus 3, all times -1.8 plus 2. So again, I'm only worried, is it positive or negative? 6 is positive. 2 times -1.8, so that's -3.6 plus 3, that's a negative number. And then -1.8 plus 2 is a positive number. Negative times positive is negative. So this number is less than 0, and so I know that it has to be decreasing on that interval. And then one more number I need to try. And so let's look at x equals 0. And so if we plug that back into the derivative, well, we get 6 times 2 times 0, so it's plus 3. So 6 times 3, and 0 plus 2 is 2. And so notice that's positive. So that's greater than 0, and so it has to be increasing here. Okay, so we found out where it's increasing and we found out where it's decreasing. So let's,
Professor,
yes?
wouldn't 0 be a critical number as well? Since it's 6 equals 0?
But 6 doesn't have, if this was 6x or 6x squared equals 0, but 6, there's no variable there. So x can never equal 0. I mean, so 6 can never equal 0. So 0 wasn't a critical number.
Okay.
You see that, Brian?
Yeah.
Okay. So we got increasing, decreasing. So it was increasing from -infinity, right? Until -2. And then it started increasing again at -1.5 to infinity. And it was decreasing in that little piece in between, which was -2 to -1.5. So remember, those are just the x values where it starts to increase and where it ends to increase, stops increasing. And so if you look back at our chart, you can tell those are critical numbers and what type of critical numbers they are. So what type of value point is happening at x equals -2? And what type of value is occurring at x equals -1.5? So we got x equals -2 is where the max occurs. Remember, it's the y value that you're looking at. And the min occurs at at x equals negative 1.5. So if you look at what is f of negative 2 and what is f of negative, or not negative, yeah, negative 1.5. Oh no. Oh well. I just had it all set up that I was just going back in and replacing it. Okay, so there's our original function. So we're looking at 4 parentheses negative 2. I'm going to do negative 1.5 first. And then I'm going to cube that. Plus 21 all times negative 1.5. And I'm going to square that. Plus 36 all times negative 1.5 minus 20. So that's negative 40.25, which makes sense because notice that negative 1.75, we got negative 40.125. And those two x values are really close and those y values are really close. So that was at x equals negative 1.5. And this was negative 40.25. And so on my calculator, I can go back in and I should be able to, if I don't push clear instead of delete, I should be able to change this to negative, or 4 times negative 2 cubed. And I'm changing it 21 times negative 2 squared plus 36 times negative 2 minus 20. So I get negative 40 there. Okay, so real quick, I want to kind of go over to Desmos and I want us to graph that and kind of look at what we had found and compare it to the graph on Desmos. So we have 4x cubed plus 21x squared plus 36x minus 20. Okay, so notice we're noticing things were happening between negative 2 and I'm going to blow this up down here. And we were having max and mins and inflection points around negative 40 something. Okay, so we noticed that it had concavity. It was concave down until we reached about, what was it? It was 1.75, right? Which is right here. And that was that y value. So if you look at to the left of that, everything gets concave down. And then if you look to the right of the point that I have on my thing, it's concave up. And so we found that by looking at the second derivative and testing on the left and the right when we found that value equals 0. And then we found that there was a max, or we saw that it was increasing until we got to x equals 2. And that max was at -40. We saw it was decreasing from x equals -2 to this -1.5. And we also saw that that point was at y value was -40.25. So we basically put all of this together by using the derivatives. Here, let's see. So I'm just gonna copy and paste this onto our document. Oops. Okay, so this was our inflection point. And this side of the graph, until we hit our graph inflection point, this was concave down. So notice when it's concave down, you can be increasing. It's increasing on the right until we hit -2 and decreasing on the, sorry, that was my left. It's increasing on the left of -2 and it's decreasing on the right of -2. And it's all concave down there. Here though, after our inflection point, we're decreasing and then we're increasing. And this whole part of the graph, forever and ever from now on, is concave up. So questions on that? I don't have the chat thing up. Okay, so pretty much what we're going to be doing and for the rest of this chapter is graphing based off of using the derivative function. And so finding out where it's increasing, finding out where it's decreasing, finding out max and min values, and then concavity. Some problems out, hold on. So let's say you're given that f of x is equal to x all over 2x plus 1. And in here, it says find the third derivative, the fourth, and the fourth derivative. So third derivative, you're just making those 3 prime signs. But anything after the third derivative, it's like you're writing the number as an exponent. And so I would write this as f, a little 4 up there that looks like an exponent, but really is not, of x. And so I noticed that I'm going to have to use my quotient rule. And I'm going to have to do this 4 times. So quotient set rule says take the derivative of the top, which is 1, times the bottom, which is 2x plus 1, minus the top, which is x, times the derivative of the bottom, which is just 2, all over the bottom squared. So let's kind of clean that up a little bit. Well, this is really 2x plus 1 minus 2x. So really in my numerator, all I'm left with is a 1 all over 2x plus 1 quantity squared. So if I want to take the second derivative, we can leave it like that and use the quotient rule. Or what about rewriting it with a negative exponent? I think that might be easier. So we could rewrite this if we wanted to as 2x plus 1 all raised to the negative 2 power. And so now when we take the second derivative, we can use that general power rule. So bring your power down front, which is negative 2, times the inside, which is 2x plus 1. Subtract 1 from our power. So that would give me negative 3. Don't forget to take the derivative of the inside. So derivative of the inside is 2. So this is the same thing as negative 4 all times the quantity 2x plus 1 raised to the negative 3rd power. So to take the third derivative, we're taking the derivative of the second derivative. We can, the way it's written, still use that general power rule, the chain rule. So I have negative 4 times the power, negative 3, all times the inside, 2x plus 1 raised to, subtract 1 from our power, it's now negative 4. Times, and I can't forget to take the derivative of the inside. And the derivative of the inside is still 2. So let's multiply out. Negative 4 times negative 3 is positive 12, and 12 times this 2 over here is 24. So I have 24 all raised to the 2x plus 1 to the negative 4th power. So one more time. So the 4th derivative, again, I'm going to use my chain rule, bring my power down front. So I have 24 all times the derivative, the power, which is negative 4, all times my 2x plus 1, subtract 1 from my power. So now it's raised to the negative 5th power, times the derivative of the inside, which is 2. So what does that give us? That's negative 8 times 24. So that's negative 192. All times 2x plus 1 to the negative. Okay, so taking multiple derivatives of something isn't bad at all. I guess it could get bad, but that wasn't too bad once we could rewrite it as using the general power rule. But what if it was same thing, but this time we're given that f of x is equal to the natural log of x. And it says part A, compute the first derivative, second derivative, third derivative, fourth derivative, fifth derivative, and then what do you think? The nth derivative of x would equal. Okay, so natural log is the easiest of the logs to take the derivative. We don't have to put in the ln of the base. And so the first derivative, well, derivative of natural log is 1 over what you're taking the natural log of, which is, in our case, is x. And then times the derivative of the inside. Well, derivative of x is just 1. So we could rewrite this. This might help us. Let's rewrite it as x raised to the negative 1 power. So when we take the second derivative, we bring down our power, we get negative 1, x raised to the negative 2 power. I'm going to list it over here in power form. 1 over x squared, but I want to leave it. I want to leave it as negative exponent over here because this makes it easier to take the derivative. So taking the derivative here of the second derivative, bring our power down front, negative 1 times negative 2. So this is equal to 2. And x raised to the negative 3rd power now. So this is 2 all over x cubed. So the fourth derivative so bring our power down front, we have negative 6, x to the negative 4th. So same thing as negative 6 over x to the 4th. So fifth derivative, well, negative 6 times negative 4, so that's 24, x to now the negative 5th. I don't want you. Okay, so 24 all over x to the 5th. So you see some, maybe we should do one more. Some pattern helping. So 24 times negative 5. And it might have helped if I had written it out each time. So that's negative 120. X to the negative 6. So what can we say about f to the nth power? Okay, well, let's look at the derivatives and see if we see any power. So, or something that we can write. So notice that this first derivative, I notice my power is 1 in the denominator. So that second derivative, I notice my power is 2 in the denominator. Third derivative, I have an x cubed. That doesn't really look like a cube, but it is. Fourth derivative, I have x to the fourth. Fifth derivative, x to the fifth. And so right now it's looking like for the nth derivative, I'm going to have x to the n in the denominator. I also notice that my signs are alternating. And so there's a way to write things when your signs are alternating. If you take -1 and you raise it to a power, so if I raise it to the first power, I get -1. But if I raise it to the second power, I square negative, I get positive. Then if I cube it, it's -1. If I raise it to the fourth power, it's positive. So it's going to alternate back and forth, just like I wanted it. So the thing is, notice here when n was 1, it was positive. When n was 4, it was negative. So I'm not sure what n is, but I need it to work for me. And so if I choose n to be 1, that would give me a -1, and I don't want that. So to make it change to how I want it to alternate, just add 1 to that number, n, or subtract 1 either way. So let me just check it. So if I plug in 1 here, first derivative, that's telling me I'm taking -1 squared, which is 1. Now the question is, how do I get this number up here? 1, 2, 6, 24, 120. Oops. I'm glad that was my calculator and not phone. I dropped something.
Would you multiply the numerator times the exponent of the denominator?
Yeah, but how are we going to write this? And I was just kind of thinking, I don't remember ever, besides my Math 10 class I'm teaching this semester, and statistics. Do you guys notice this is actually factorial? Notice that so basically what n factorial is, let me just write this. Basically, you're multiplying the number up until you hit n. So for instance, if I had 2 factorial, this is saying I'm taking 1 times 2, which is 2. If I had 3 factorial, this is 1 times 2 times 3. So if I just take the number above 2 and multiply 3, that gives me 6. If I have 4 factorial, this is equal to 1 times 2 times 3 times 4. Let me just take the number above, because that's 1 through 3 multiplying together, times 6. This is 24. So if I look at 5 factorial, guess what I'm going to get?
120.
Yep, 120. And so I notice that I can express that number that is up in the numerator by a factorial. And so here I can say this is in factorial. Would that work? Let me just make sure. Because I'm going to have to manipulate a little bit because my first two terms, notice, are 1, 1. Then I get to 2 and 6. Okay. So another rule for factorials is that 0 factorial is equal to 1. And so if I rewrite this up in here, instead of writing it as n factorial, if I write it as n minus 1, and then take the factorial. That would manipulate it so I have the right things in my numerator when I wanted. And so for instance, let's just look at the n minus 1 factorial. If I put in the first derivative, n is 1, so I get 1 minus 1 is 0 factorial, which is our 1. Then if I plug in n is 2 for our second derivative, I get 2 minus 1, which is 1 factorial, is 1. Might as well put that there. If I plug in 2, I get the third derivative, right? I get 3 minus 1, which is 2 factorial, is 2. So those are getting me the right numbers up there, and I have the right thing to get me the right sign. So we actually came up with a formula if we wanted to use it. I probably would not. Well, maybe I would. So based off our formula, let's say we want to find f of 950. Oh, actually, our calculator's not going to like that. Not one bit. Okay, we're just going to leave it in factorial. If you put that in the calculator, it's going to probably spit out an error. It's too big. Which, let's see if I have it on here still.
Do you want to learn to draw professional and impressive artwork from scratch that
Hold
will
on.
blow people's minds? I'm Scott Harris, professional illustrator, painter, and artist. My character drawing course on Udemy has helped thousands of students.
I just something yesterday. I don't think this is it. Oh, well. Hold on.
A number of different ways.
Okay, so I'm going to try something. Let me see if I can share this video with you guys. I think I have to change a setting on here. Did you guys hear when it was playing the sound from the video?
Yes.
Or just me talking? You did hear the sound of the video?
I do hear the sound.
Yeah, we can hear the video.
Okay. Someone was having problems with that. Maybe I hooked it up. So just because I was talking about factorial and I just saw this video yesterday and I didn't realize I was going to show it to you guys. If anything, I was going to show it to my Math 10 class because we're doing probability. But think about if you multiplied 1 times 2 times 3 times 4 times 5 all the way up to 52 and what type of number you would get. And so this video kind of explains that. So let me play that for you.
How many games of chess?
Oh, let me skip this.
There is a popular fact that the number
That's
of games
not
of
what I
chess
wanted.
is greater than the number of atoms there are in the observable universe. This is a fact. Is it true? The number of different ways 52 cards can be arranged. There's obviously a lot. The top card could be any card. So there's 52 different possibilities. Any remaining cards can follow, so there are 51 possibilities for the next card. 50 for the third spot, 49 for the fourth, and so on.
Did you get that?
Kind of muffled.
Yeah, it was kind of jumbled.
Well, first of all, I had it play speed back was 1.5. So we go to normal. Oh, let's try this one more time. It might be better. Let me get the volume up if I can. See if that works.
The number of different ways 52 cards can be arranged. There's obviously a lot. The top card could be any card, so there's 52 different possibilities. Any remaining cards could follow, so there are 51 possibilities for the next card. 50 for the third spot, 49 for the fourth, and so on. Multiplying all of these numbers together gives us how many unique ways 52 cards can be arranged. 52 factorial is a gigantic amount. So large, in fact, every time you shuffle a deck of cards, well, swoosh it for a few minutes or ripple it 7 or more times, chances are you have put those playing cards into an order that they have never been in the entire history of cards, or humans, or the universe. Seriously. This is because 52 factorial is 8.0658 times 10 to the 67th. In comparison, the observable universe is only about 10 to the 18th seconds old. Even if you had been properly shuffling a deck every single second since the universe began 13.7 billion years ago, you still to this day wouldn't have even come close to assembling every arrangement possible. But even that doesn't paint the whole picture of just how big 52 factorial is. Scott Cheefield wrote what, in my opinion, are some of the most mind-boggling visualizations of the size of 52 factorial. Imagine setting a timer to count down 52 factorial seconds. While the timer runs, stand on the equator and wait 1 billion years. After a billion years have passed, take a single step forward, and then wait another billion years before taking a second step, and so on. Once you have walked all the way around the Earth, take a single drop of water out of the Pacific Ocean that's 0.05 of a milliliter and set it aside. Now continue walking at a rate of 1 step every billion years, removing 1 drop after every journey around the entire Earth, and by the time the Pacific Ocean is completely empty, put a single sheet of paper on the ground. Refill the ocean and keep going until the stack of paper reaches the sun. At that point, how many seconds will be left on the timer? Will it be 0, a few hundred, a few billion? No, there will still be 8 times 10 to the 67 seconds left. You have barely made a difference. If you start and do that whole thing 1,000 more times, you will only be a third of the way done. Luckily, Scott has a great idea for how to pass the rest of the time if you're bored of paper and water and walking. Instead, he says, deal yourself 5 cards every billion years. When you finally deal yourself a royal flush, buy a lottery ticket. If the ticket wins the lottery, throw a single grain of sand into the Grand Canyon. As soon as the Grand Canyon is completely full of sand, remove 1 ounce of rock. That's about 28 grams from Mount Everest. By the time Mount Everest is level, take a look at the clock. This is what we want. Do the whole royal flush lottery ticket Grand Canyon Mount Everest thing 256 more times, and then, and only then, will your timer have reached 0. That is how big 52 factorial is. But now think about this. The number of possible people, the number of different humans there could be is, well, even larger. What that means is that even though you will probably possible person won't even get to die like you do. They won't even. So, I'm glad you were. And as always, thanks for watching.
Okay, so does that give you some sort of idea of what 52 factorial was? And what did I say? I wanted to do 950th derivative. And so that 950 factorial, there's, yeah, our calculator wouldn't compute it.
So it's pretty big.
Yeah, it's huge. But we can express it with
Plugged it into my calculator and it said overflow error.
yeah. Exactly. So, but we could express it with 4 digits. A 950 and an exclamation mark. Anyways. So that was a sidetrack off of me randomly choosing what huge derivative we were going to take. And so let's just take it real quick and express it. And so basically we're going to take -1. We're going to raise it to the 950th plus 1. So we're going to raise it to the 951st. We're going to take 950 minus 1. Actually, it only had to calculate, Krista, 949 factorial. Maybe it can handle that one. All over.
I plugged the whole function in just
Right.
like it is on my calculator and it
Yeah.
still said overflow error. So
Yeah,
it wasn't
of
going to do
course.
it.
I'm just joking with you. And x is raised to the 950. I can clean it up a little bit. I know if I raise -1 to an odd power, that result's going to be negative. Oops. It doesn't like that. Okay, anyways, so this is negative. I'm just going to leave it like that. You guys need a break? Should we take a 10-minute break?
Yeah.
Okay. Okay, so I will see you guys in 10 minutes. Let me pause the video. Okay, so during break, I was able to put some more things onto my Word document that I was writing on. And so we were talking about inflection points. And I told you that an inflection point is where you're changing concavity from concave up to concave down. And so in this case, we are concave up. And then we're changing position. And so this is our inflection point.
You want to share your screen? We can't see what you're writing on.
Thank you. So here are some examples of where graphs are changing from concave up and concave down. And looking at the point where it changes, we talked about was called the inflection point. Notice that in the example 2, that change in inflection we're increasing still. So we're increasing all this way. Here, notice that change in inflection. So this change in inflection, actually, these are different things I should talk about. The first change in inflection, notice that this has a slope. Here, a positive slope. Here, that's not 0. Here, our slope is 0. And here, our slope, it's undefined. Okay. So let me just kind of read through this. So definition of point of inflection. Let f be a function that is continuous on an open interval. We're going to let c be the point in the interval. If the graph of f has a tangent line at this point c, f of c, then the point is a point of inflection of the graph of f if the concavity of f changes from upward to downward or downward to upward at that point. We would say if that happens, then that c, f of c is the point of inflection of the graph of f. And when we did this, either f double prime of c was equal to 0 or f double prime of c was undefined. So other thing that this chapter talks about is finding max and mins. And so one way that we were finding where a maximum or minimum point were occurring was where we were looking at the first derivative test and we were trying to find, was the graph increasing or decreasing? Where was it changing direction? And by that, we could tell if a max or a min occurred at that critical point. We can also use the second derivative test to find if a critical point is a max or a min. And so there's two ways that we can determine if a point's a max or min. One was the way that we learned before, increasing to decreasing or decreasing to increasing, or the second derivative test. So to use the second derivative test, we're going to do the same thing as before. We're going to look at when is the first derivative equal to 0 and where does it not exist. Once we find those critical numbers, instead of testing each side of it, we're going to plug it into the second derivative. If we find that the second derivative, when we plug that critical number in, is positive, then it's concave up, and this tells me that it is a minimum point. If I find that the second derivative at my critical value is negative, it's concave down, and that would tell me that my critical point was a max. So if for some reason you use the second derivative test and you get that the second derivative is equal to 0, that test doesn't tell me that c is a max or a min. The test doesn't work and we can't tell. It's possible it's a max or a min. We have to use the first derivative test to try. So here's an example. And so we're going to find where the max and the min occur. When it says relative extrema, it's just saying that you're trying to find where is the local max or local minimum values. And so looking at f of x, I'm going to first find my first derivative. And so taking the derivative of negative 3x to the 5th, I get negative 15x to the 4th. Plus, and so taking the derivative of 5x cubed, I get back 15x squared. So I need to find where f prime of x equals to 0. And so I'm looking at when is negative 15x to the 4th plus 15x squared equal to 0. So to solve for when this is 0, I'm going to factor. So notice that both of these two terms have a 15 in common and both of them have an x squared in common. So let's pull out a 15x squared and let's pull out actually a negative 15x squared. So if I pull out a negative 15x squared, the first term would be left with just an x squared minus, and if I pull out a negative 15x squared from that second term, I'm left with a 1 equals 0. So looking inside my parentheses, I noticed that that factors further. There's a difference of squares there, x squared minus 1. So that factors as x minus 1 times x plus 1. So set each factor equal to 0. So negative 15x squared equals to 0, x minus 1 equals to 0, or x plus 1 equals 0. So I find my critical numbers are x equals 0, x equals 1, and x equals negative 1. Okay, so now I need to figure out what my second derivative is because I'm using the second derivative test. And so now we want to find the double derivative. So I'm just going to shrink this for a second. So looking at the double derivative, so I'm looking at when is the derivative of negative 15x to the fourth. So 4 times negative 15 is negative 60, x cubed, and then plus 15 times 2, which would give me 30. X. Okay, so I'm using the test to see if we have a max or a min. And so we want to plug in our values into the second derivative. So plug critical numbers into f double prime of x. And so if we plug in 0 into the second derivative, well, that gives me negative 60, right? All times 0 cubed plus 30 times 0. So doing that, this is equal to 0. Well, if I get back 0, unfortunately, the test is inconclusive. That doesn't tell me anything. I have to go back to the first derivative test. Okay, so before we do that, let's check the other two. So if we plug in 1 or negative 1 into the second derivative, we get negative 60. Let's plug in negative 1 first. Negative 1 cubed plus 30 times negative 1. So this is going to give me positive 60 because negative 1 cubed is negative 1 times negative 60. So that's positive 60 all plus negative 30, or 60 minus 30, which is 30. It's greater than 0. That means it's concave up, which tells me x equals negative 1. A local min occurs. So we have a local min occurs at x equals negative 1. So we can find what that value is, where the local min is, because it's the y value, by plugging that back into our original function later. And then we want to look at one more, the double derivative, plugging in +1. And so we have -60 all times 1 cubed plus 30 times 1. And so that gives me -60 plus 30. So this is -30, which is less than 0. That tells me the concavity less than 0 is this way. So I have we have a minimum, I'm sorry, a max. You have a max at x equals +1. So local max at x equals 1. So we now need to test x equals 0. Okay, so be careful here because we had some critical numbers. And so things can change on different sides of critical numbers, right? And we had critical numbers at 1, -1, and 1. So when we test values on each side of our 0, I want it to be between my critical numbers. So I need to choose something between -1 and 0. And remember, we're plugging this back into our first derivative. So if I plug in -0.5, wherever I see an x in my first derivative. And so let me pull back what my first derivative was. And that was -15x to the 4th plus 15x squared. So this gives me -15 all times -0.5 to the 4th plus 15 all times -0.5 squared. So if we do that, actually I can tell it's not going to work. If we do this, we get that this is approximately 2.8, which is greater than 0. And so this is increasing. But notice if we plug in +0.5, we're going to get the exact same value. Because when we were plugging this in before, we were raising our value to an even power, which made it positive. And so I know I get back approximately 2.8 again, which is greater than 0. So if I have something that is increasing on the left of 0 and increasing on the right of 0, then what do I know about what's happening at x equals 0? So because it's increasing and it's not changing direction, it's neither a max or a min there. So any questions on that? Should we try to do one more problem or should we call it quits for today? If you guys are chatting, I can't see it.
Nobody's chatting.
Okay,
I'm good.
you guys are good. Okay, so let me pause this.